Let's now apply our fundamental definitions of work and potential energy to point charges. So we'll start with big Q. So big Q here is a charge that's producing an electric field, and that protrudes or emanates radially outward from Q. So we're going to consider a line radial here, and two positions A and B. So we have radius A and radius B. And now we're going to put a test charge, little q, within this path, and we're actually going to move little q from A all the way over to B and figure out how much work the electric field does in doing so. Now Q0 is small enough, this little q is small enough so it doesn't disturb the charge of Q itself. Kind of like with masses. It doesn't, a test mass is small enough not to produce a tidal effect on the source mass. Well, this Q is small enough that it doesn't produce a change in charge distribution of Q. All right. Now, there is an electric field at A and an electric field at B. It's an inverse square law, so at B it's a lot smaller. The electric force from two charges, as we've already learned, is KQQ over R squared. So the work in moving little q from A to B as a result of the electric field produced by big Q is simply the integral of F dr from A to B, RA to RB. Now the force is radial, so I put F rad. And it's always in the same direction as dr along this path, so it's a real simple scenario. We don't have to worry about cosine of theta in this case, it's always 1. So that's QQ over 1 over 4 pi over 4 pi epsilon 0. Integral of 1 over r squared is negative 1 over r from RA to RB. And that gives us QQ over 4 pi epsilon 0, 1 over RA minus 1 over RB. Now that work from the mathematical equation is positive or negative depending on the relative signs of these charges. So in this case, like in the case, where they're both positive, then this whole thing is positive. Well, what's this? Well, RA is smaller than RB, so this is always positive. This is a bigger number than this number. If these are opposite signs, then this whole thing is negative because they're pulling on each other. If they're both the same sign, these two charges are pushing on each other, so that's positive work done by the force field. So hopefully that is quite clear. Now let's consider the general case for point charges. So in general, we have our Q, point charge big Q, producing a diverging electric field in three-dimensional space, and we're going to put little q in that field somewhere. Now it's got some radius r and producing a force F radially out from big Q, acting on little q. Now let's consider 2 points in this field, A and B. Notice they are not radial with respect to each other. We have 2 different radii that these locations represent, and we're going to consider a path between them. We got RA, we got RB. Path between them could be any arbitrary thing. So let's choose this path. Yeah, that's a good path to choose. Now at the point of Q right now, where Q is, there's a DL. So DL is just simply the differential path length at that point, and it's a vector of infinitesimal size in a spatial direction that the path represents. Let's look at this scenario in magnified form. So here's our Q. There's a radial line, and here's the force right there. And now dl is just magnified here, and of course F dot dl are 2 vector quantities, and the angle between those 2 vectors is theta. So any path that we choose, this analysis is the same. And the work in moving the charge to A to B is going to be the integral of F cosine of theta dl. Notice that dl cosine of theta is this little quantity here, the radial part. So really, cosine of theta dl is dr. It gives us this. So there is dr. And now we can see why along any path it doesn't matter. We could have A being over here and just go in a direct radial path, or as we integrate this path, as we do the line integral, the way cosine of theta dl works, when we integrate that, it's always taking the radial part and multiplying it by the force at that point. So it ends up not mattering what path we choose. So we get as a result QQ over 4 pi epsilon 0, integral 1 over r squared. We've already done that integral. It looks like this. Now, that's UA minus UB. Work from A to B is UA minus UB. What we can see is this is UA. All right? This whole thing is negative delta U. But this is UA, and what's UB but this part? So how do I draw that? Woo, like this. Wow. There we go. So UB is that. And it's UA minus UB. So UE, electric potential energy, is KQQ over R. Doesn't that look familiar? Remember, U sub G is big G, big M little m over R. And for the same reasons, and by analogy, the electric potential energy has the same form for a point charge. So we have a couple ways of interpreting this result for the electric potential energy between 2 point charges, big Q, little q. We've just defined it as the work done by the electric field of big Q on little q in moving the little q from A to B. But U as an external agent could grab Q and shove it back toward big Q. And that would be equivalent. So an external force moving little q from B back to A. Now if the q's have the same sign, that work is positive because you as an external agent have to shove them together. If they're the opposite sign, these two charges are going to try and attract each other, so you got to hold q back, pulling back on it to keep it from going in that direction. But if it does move in that direction, then the work done is negative. And that's the same thing as with the electric field force. If these two are the same sign, they shove apart on each other, and that produces positive work as well. Now, where is the potential energy equal to 0? Well, where this goes to infinity. Same scenario as with our consideration for gravitational potential energy. And now how do we handle multiple charges? Not too hard. So here we have multiple charges, and there's energy associated with each charge compared to the other, or the whole system for that matter. So two considerations. First of all, we're going to figure out what is the electric potential energy of Q0 with respect to not just Q1 or Q2 or Q3, but all of them. There's potential energy with respect to all of them. And to figure it out, you just add them. You add the potential energies of each one. That seems very reasonable. So we take the potential energy between these two, calculate it, calculate this one, calculate that one. We can write that as the sum of each one of those, where KQ0 factors out. And the uniqueness comes in, well, the other Q over its radius plus the other Q over its radius, etc. And so that is the formula for the potential energy of a point charge with respect to multiple other point charges. Work by the E field to move Q0 to infinity is what that is. Or it's the work done by the external force to take the charge Q0 from infinity and move it all the way back into position. That'll be the same number corresponding to the same electric potential energy. But that's just worried about Q0. You move Q0 infinitely far away, these guys are still have a close proximity, so they have energy with respect to each other yet. So what about the energy of the entire system? Well, that seems like that could get a little complex. We took care of this guy. But now we have to do that for the other ones as well. Well, the combined effect of all that is the potential energy of the system, which is given by K times the sum of the products of all these, but you don't want to consider anything twice. So it's going to equal the work done by the conservative force to move all the charges to infinity, not counting any twice. And that's made sure when we multiply 1 by 2, we don't do 2 by 1. So 1 by 2, 2 to 3, and of course 0 to 1, but we don't reverse the numbers. So adding all those will give us the correct value for the system potential energy.